Hey folks, welcome to the video number one in our 10.3 Taylor series operations lecture series. So in this video, we're going to talk about recognizing some basic Taylor series, all right, at zero. And then we're going to focus on finding Taylor series as well as intervals of convergence using addition and multiplication properties, all right? So we'll have that in video one. In video two, we'll take a look at finding Taylor series and interval of convergence using differentiation and integration properties. And in our last video, we'll take a look at finding Taylor series and intervals of convergence using substitution. All right, let's get started. So we've got a nice table here of your basic Taylor series. All right, now I just want to say that I will provide these on the exam. So let's make a note. Judy will provide these on exam 3. Okay, so I will provide these on exam 3. You don't need to waste precious space on your reference sheet to write them down. So I'll give you a sheet with these. That might still mean that I ask you to show me how you get from here to here using our earlier lessons with Taylor polynomials and Taylor series. But at least you'll know what the answer is, but we'll also focus on some of the operations that we're going to do in this video. Okay, so got our basic Taylor series. Hopefully these look familiar by now. We've got a 1 over 1 minus x, 1 over 1 plus x. Both of these have an interval of convergence between -1 and 1, and they look very, very similar, except there's a sign difference. All right. In fact, we might even say that this second one is an alternating series where like one term is positive, one term is negative, one term is positive, one term is negative. All right. And we actually might see the same pattern for natural log of 1 minus x and natural log of 1 plus x. All right, so we can see in the 1 minus x that every term is negative, but as soon as we get to the natural log of 1 plus x, we see the alternating signs. Okay, and the alternating means that somewhere in our series we should have a -1 to the n, or like a -1 to the n minus 1, something to show that like the signs keep changing. Okay. Last but not least, we've got e to the x and e to the negative x. Again, e to the x is all positive terms. Don't forget about those factorials on the bottom. And then our e to the negative x is another case of our alternating series. And we see that -1 to the n term. Okay. Of these 6 key ones that we tend to see a lot, only the exponential ones are converging everywhere. The other 4 only converge between -1 and +1. Okay. All right. Well, let's move on to some examples. We're going to start with our addition property. Okay. So we've got some good news for you. The addition property, when we're adding two Taylor series at 0, work exactly the way we want it to, meaning we can literally just add term by term by term. Okay. Now I like the way that this formula is laid out, but you also don't have to get too hung up on the formula, because I think it'll become clear as we're doing it what we mean by adding term by term. Right. So there's an A0 and a B0. Neither of those have an X, so we could clump those together. Right. Now, A1 is a coefficient of X and B1 is a coefficient of X, so we can add them together, A1 plus B1, with the X, all right? Same thing, we could think about our A2 goes with the X squared, B2 goes with the X squared, so then we have A2 plus B2 to the X squared, right? And what we're really looking for here is that we can add A sub n plus B sub n from the two series together, and they'll be the coefficient for our x to the n, all right? Now, one thing we probably do want to know, this operation is only valid in the intersection of the intervals of convergence. Okay, so we'll make more sense of that when we take a look at the two examples, but it has to be the place where they both are true. okay? It can't be the place, like the interval of convergence can't just be where one of them is converging. It has to be where they're both converging, okay? All right, so let's start with question number 1. Find the Taylor series at 0 for f of x equals e to the x plus natural log of 1 plus x, and find the interval of convergence. All right, so I notice that I've got my e to the x and I've got my ln of 1 plus x, all right? So e to the x is my first Taylor series, and my ln of 1 plus x is my second Taylor series. And I can see from here very clearly that I'm adding them together. So let's take a look at our Taylor series for e to the x. So if you turn back to the other page, you'll see that it's 1 plus x plus 1 over 2 factorial x squared plus, we could even say 1 over 3 factorial x to the 3 plus, we keep adding until we get to 1 over n factorial x to the n, and then we keep going, okay? Now, let's take a look at our natural log of 1 plus x. So natural log of 1 plus x. Same thing, if we turn back to the other page, we'll see that this is actually 0 plus x minus 1/2 x squared plus 1/3 x cubed. Well, the next one would be minus. We keep going and we get to negative 1 to the n minus 1 over n x to the n plus a bunch more terms, okay? Now, I know that you're probably saying, Judy, there was no 0 on the other page. Why are you writing extra numbers? And part of that is to set myself up to be adding my terms that are in the same location, okay? So what I mean by that is when I'm adding these, I'm going to do 1 plus 0. That's going to be my first term, okay? So for f of x equals e to the x plus this natural log of 1 plus x, I'm going to get 1 plus 0, okay, plus, okay, 1x plus 1x, like those I can combine. So I get 1 plus 1x plus, all right, what are the coefficients for the x squared terms? 1 over 2 factorial minus 1/2. Those are the terms that have the x squared. So I'm going to write that as 1 over 2 factorial minus 1 over 2 x squared. Okay? I'm going to write out one more of these. Let's go to the third power, see what we get. So plus, all right, what's the third power? 1 over 3 factorial plus 1 over 3. 1 over 3 factorial plus 1 over 3x cubed. And I can keep going until I get to the x to the n power. And so this might look a little weird, but I'm just going to write this as 1 over n factorial plus negative 1 to the n minus 1 over n x to the n. Okay? So I hope we can kind of see how in each one I've got the terms from the e, or the coefficients from the e to the x. All right, that's the first one in every single one. And I'm just adding it to the first term in the natural log one. And that's where the 0, the 1, and minus 1/2, the plus 1/3, and ultimately where this comes from. Okay? Now we do want to add a plus dot 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 because it keeps going forever. But let's clean this up a little bit, okay? I think a lot of the questions on your homework will ask you to write like the first 4 terms. So we want to make sure we get 4, and then it'll ask for just the general formula, okay? So if this were a homework question, I might do like 1, because 1 plus 0 is 1, plus, let's see, 1 plus 1 is 2x, plus, and I would leave this as 1 over 2 factorial minus 1/2 x squared plus 1 over 3 factorial plus 1/3 x cubed. So like these coefficients here, 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 and here are what I would type in if I was talking about the first four terms. Then they're going to ask for the nth one. So I'll just leave that in the unsimplified form. Okay. So it's a lot of writing. I'm not going to lie. This is a lot of writing, but all we're doing is we're adding the same terms from both series. Okay. Now, before we take a look at question number 2, though, let's see if we can find our interval of convergence. So earlier I said that the operation is valid in the intersection of the intervals of convergence. So our interval of convergence for e to the x is negative infinity all the way to positive infinity, like it converges everywhere. But for the natural log, it only goes between -1 and +1. We have to choose this part where they both are true. And the only place where they're both true is from -1 to 1. Because anything bigger than 1, only e to the x converges, this one diverges. And anything less than -1, this one converges, but the natural log one diverges. Okay, so our interval of convergence, I'm going to squeeze this in the corner over here, is just from -1 to 1, because that's where they, fancy word, that's where they intersect. Okay. All right, let's try another one. Again, it's going to be a lot of ink. We're going to write down the first series with the second series, and then we're going to add them term by term. Okay. All right. Example 2, find the Taylor series at 0 for f of x equals 1 over 1 minus x plus 1 over 1 plus x, and find the interval of convergence. So we've got 1 over 1 minus x. This one is 1 plus x squared plus x cubed plus all the way x to the n plus, and I keep going. And this one has an interval of convergence between -1 and +1. Now, remember we were talking earlier about how 1 over 1 plus x is very similar, except this one is an alternating series. All right, so we actually start with 0 plus x minus, oh, sorry, not 0. What am I doing? 1 minus x plus x squared minus x cubed plus, I'm going to keep going. I can't just write x to the n here. I have to do the -1 to the n. That gives the alternating sign, x to the n plus. Now, good news for us. This one has the same interval of convergence as the other one. So where do they overlap? It's just going to be right there. Okay, so our interval of convergence for this one is just from -1 to +1. All right, so if we were to write our f of x for this 1 over 1 minus x plus 1 over 1 plus x, let's add them term by term. Okay, so we've got 1 plus 1. That's going to give me 2. And then I have positive x and then negative x. Well, that's going to give me 0. Ooh, this is looking interesting. Okay, then I have x squared plus x squared is going to give me 2x squared. Okay, and then x to the third minus x to the third gives us another 0. Okay, so it seems to me what's happening here is we're like skipping powers, like all the odd powers are zeroing out, but all the even powers, now there's twice as many of them, right? X squared, now there's 2 of them, but like x to the third, gone. I bet there's going to be 2 of the x to the fourth, and the x to the fifth is going to be gone. And then there's going to be 2 of the x to the sixth, and the x to the seventh is gone. Okay? So the way we would continue to write this is we would say 2x to the 2n. Like we're just skip counting, right? We're counting by twos. 2, 4, 6, 8, 10, whatever this 2n is, okay? Plus, we keep going. All right, now let's clean this up a little bit because when we say type in the first four terms, we don't mean like 2, 0, 2x squared, and 0. We mean the four non-zero terms. So 1, 2, 3, 4. Okay? So we would say 2 plus 2x squared plus 2x to the fourth plus 2x to the sixth plus all the way to 2x to the 2n. And my interval of convergence is just going to be that -1 to 1. Okay. All right, let's get that all on one page for you. But this is our addition, okay? Works exactly how we want it to. Let's take a look at multiplication. All right, so property number 2 says that a Taylor series at 0 can be multiplied term by term by an expression of the form cx to the r. Okay, so in other words, we're really looking for there to be a polynomial on the outside or a power function. Okay, it does need to be an integer though. So R can be like 1, 2, 3, 4, 5, but it couldn't be like 1/2. It couldn't be like -7. Okay. So it has to be a non-negative integer. And when this happens, all we do is we take the Taylor series that we have and we just multiply it by whatever that cx to the r is on the outside. Okay, and it will turn out that this Taylor series will have the same interval of convergence as the Taylor series for f. All right, let's take a look at an example. Example number 3, find the Taylor series at 0 for f of x equals 2x squared. Oh, there's that non-negative integer times e to the x, e to the negative x. And e to the negative x, I know, is on our table from the front page. So we can say e to the negative x. Ooh, this is one of those alternating ones. We have 1 minus x plus 1 over 2 factorial x squared minus 1 over 3 factorial x to the third plus, and I keep adding until I get to -1 to the n over n factorial x to the n. Now this one has an interval of convergence everywhere from -infinity to +infinity. So my Taylor series for my f of x is going to also converge everywhere. All right, let's multiply it out, just like that property says. Our f of x is equal to 2x squared e to the negative x, which means we're going to take 2x squared and we're going to multiply it by this whole thing. All right, what does that get us? 2x squared times 1 minus x plus 1 over 2 factorial x squared over 1 minus 1 over 3 factorial x cubed plus -1 to the n over n factorial x to the n. And I'm going to keep going. All right. The only thing we have to do, again, if this is a homework question, just distribute however many terms they tell you, which is usually 4. We're just going to take this 2x squared and we're going to distribute it to all the things on the inside. All right. 2x squared times 1 is 2x squared. 2x squared times -x is minus 2x cubed. 2x squared times 1 over 2 factorial x squared. Let's do the numbers first. 2 over 2 factorial, and then x squared times x squared is x to the fourth. Minus 2 over 3 factorial, x to the 2 plus 3 will give us 5. Okay, plus 2 times negative 1 to the n over n factorial x to the n plus 2. Now, here's a hint that I hope will be helpful. I think a lot of times in earlier math, we're used to just using our calculator and dividing out the numbers, which has its time and its place. But I think especially when we're working with series, the it's a fine line between simplifying and simplifying too far. You almost want to simplify just enough so that you can still write your pattern with n. Okay, so if I take 2 divided by 2 factorial and I turn that into a decimal, and then I take 2 divided by 3 factorial and turn that into a decimal, writing this term is going to be a lot harder. Okay, so usually if it's in a fraction form, keep it like a fraction. If there's 2 fractions, try and multiply them together so they're in 1 fraction. Okay, and then if there's factorials, leave those factorials because you're just going to turn that into n factorial anyway at the end. Okay. All right, all of this to say this is our Taylor series for the given function, and our interval of convergence is the same as our e to the negative x, which is from negative infinity to positive infinity. Okay, so that's it for the first video. Come on back for the second, where we're going to take a look at differentiation and integration.